Alright, welcome to another AQA A-Level Chemistry video. Today I'm going to be doing a video on benzene. The last video was on acetylation. Benzene is one of my favorite. It's more to do with the structure and reactivity, right? It includes benzene. But we've now gone to like this part about benzene. This compound is really much about aromatic compounds. And when we're talking about aromatic compounds in year 2 organic chemistry, the one that you have to know. And generally benzene is the one you have to know is benzene, right? But benzene comes up in pretty much nearly all of year 2 organic chemistry. I say all of it, but like it's quite an instrumental part of it. It's quite a big part of it, even though you might not have to understand all of it, but you have to like you'll see it come up quite a lot, even if it's not really part of a reaction, but you'll see it come up. It's usually a part of compounds. A lot of these big compounds that you need to know, that you be aware of, they'll have a benzene ring. And you probably say, what's that circle inside of a hexagonal ring? And that's benzene, right? In year 1 organic chemistry, you probably see it. Is it part of aspirin? I'm not going to say it's part of aspirin in case it's not. I think it is part of aspirin. Not important for that point. But yeah, this is benzene or structure and reactivity. But generally, this topic is about benzene. It's probably one of my favorite parts of chemistry. It's very interesting. The benzene in itself is a very interesting compound in the way it keeps itself. Yeah, it's got a bit of history to it, a bit of a bit of an odd history, but not an odd history, but an interesting history to it. But yeah, the reason why it's important to understand benzene before I start go into the video and talk too much in the introduction. Then why it's important is that it has a 6-mark question in it. Where you have to talk about you have to essentially talk about how it's able to keep its structure and how it's different to its counterpart, which is another compound called cyclohexyl-1,3,5-triene. I'll get through into that, and you have to also talk about you have to actually do the mechanism. So there's a 6-mark question about talking about its structure and how it's stable, and there's another 5-mark question where you have to do the mechanism for it, which I'll also go into it. But yeah, I feel like a lot of people, when they watch these videos or study benzene for the first time, look like it's a lot to understand, and it may be a bit difficult to understand. But one thing you need to understand one thing you need to understand about just chemistry in general, like all these hard topics, right? There's not actually, now I'm saying this as someone who's already done my exams, but the honest truth is, if you want to understand how to do topics, the best way to do it is doing exam questions, and that's especially true for this topic. Once you understand how to answer benzene, it makes your life so much easier, because it sounds like a lot, but once you really get to it, it's really easy to remember. But yeah, the most important thing about before I start going into the video, if you want to understand if you want to understand a topic, right, the best way to do it is by answering exam questions, not reading notes or looking at your thing or doing these little quizzes on the side. The quiz, like, that's not testing yourself. What I mean testing yourself is actually doing exam questions. And the best way to understand this topic is to do exam questions. I'm going to go through the content of this video, but the only way to actually understand this topic really and truly and nail it on is by being able to answer those exam questions. You might not get it right the first time, and that's okay, but consistently trying to answer these exam questions, and you'll get it. But yeah, I'll shut up now and actually get straight into the video now. Yeah, so benzene has a cyclic and planar structure formula C6H6. C6H6 has a very similar molecular formula to that of cyclohexyl-1,3,5-triene. I'll show you that later, but its reactivity is different from other unsaturated compounds. So this is what it looks like. Yeah, I'll come back to this here, but I'm gonna go through talk about this compound here before I actually explain this picture here. So the structure of benzene. So benzene has delocalized p electrons. This makes benzene aromatic and more stable than its non-delocalized equivalent cyclohexyl-1,3,5-triene, as I said before. So benzene has this hexagonal planar structure with its p orbitals above and below the plane of the ring. Okay, so I think I'm kind of getting to a point where people might not understand what I'm talking about. So now I think it's perfect time for me to actually jump in. So what benzene is? So this here is this isn't what the structure of benzene is. This is a 3D model of what benzene is. remember in chemistry when we're talking about when we're drawing out compounds and we need to give you the 3D structure, we always show the 3D structure because that's good. Compounds are 3D. Some compounds are 2D, but this is though it's planar, it's in space, so it's 3D. And this we're showing that this is a 3D compound by having this wedge line here, showing that this part of the compound is closer to us compared to this side here. That's all it is here. You don't actually have to know this. This is just a 3D compound I've given you here. I drew that. And these here are the p orbitals above and below the plane of each carbon on the carbon ring, or the benzene ring. So what I think the best way of explaining this still, I should show you the Kekule model, which I'll go through there. Kekule is just the name of the guy that discovered it. Yeah, bit of a spoiler. I said it right there, but I was going to go into that. But anyway, benzene has a hexagonal planar structure with its p orbitals above and below the plane of the ring. And to be aromatic, the p orbitals must overlap. This is why structure is planar, so the p orbitals can overlap. So these p orbitals overlap and allow the structure to be planar. Because the p orbitals overlap, consist above and below the plane, it kind of keeps this structure. And it's also to do with something about it having something we call a pi system. I should go and actually explain it now. So now actually I can actually go and explain what I mean, right? So this looks, right? This looks, and it's actually this in itself, right? It looks like, and probably can be represented, and you can actually. This is, I'll even say it, right? This is cyclohexa 135 triene, right? In terms of what it looks like, cyclohexa 1,1,3,5-ene, right? But this is actually benzene. And now cyclohexa 135 triene theoretically exists, but in reality doesn't exist. The reason for it, right, is that each carbon, as you can see here, has 3 bonds, but the carbon next have 4 bonds, right? So each carbon has 3 bonds and it donates 1 electron into the carbon ring. And also these are, remember when we're talking about double bonds in chemistry, when we're talking about alkenes, right? They have the pi bonds, right? So here in benzene, it has 3 bonds. Each carbon atom has, this is the structure. This is one thing you need to know. So each carbon atom has 3 bonds and donates 1 electron to form what we call a delocalized pi system. Delocalized because the electron that's given in is delocalized, is free moving, kind of like with a graphite, right? Graphite has 3 bonds. Graphite is not this structure. Just want to make that clear. Graphite is not this structure, but just say like how graphite has 3 bonds and it donates 1 electron, and that allows delocalized electrons to freely flow throughout graphite, right? And here it's a similar principle where each carbon atom has 3 bonds, not bonded in the same way. Obviously, it has double bonds here, but these are pi bonds. There's our bonds here, pi bonds, and what was that? Yeah, these are pi bonds. So each carbon atom has 3 bonds, and 1 electron is donated to form a delocalized pi system. What does that actually mean? Well, that actually means that the delocalized pi system actually allows for something that we call resonance, where with cyclohexa 135 triene, right, these bonds would stay as they are, here, but what they actually are allowed to do is that they're allowed to resonate, or the word's called resonance. I'll kind of go into that later, but they're able to do this. So this bond will actually shift to here, this bond will shift to here, this bond will shift to here. And it's constantly switching all the time. All the time it's constantly switching. And that's called resonance. And that's because, and that's what that does, what the reason it does that is to allow aromaticity, allow its structure to be to exist. The reason that someone discovered this compound and it realized it had weird properties, and it didn't match the typical properties of what is known as cyclohexyl 135 triene, it didn't match those properties, but it matched this property where it had say it had one property that they couldn't explain, which is the enthalpy of hydrogenation. I'll go through that. I'm gonna go through how they prove that this compound exists and all that, because that is one thing that you need to do for exam. One of the things that you need to kind of go through. But the reason why this was deemed to be a stronger compound, because this is a stronger compound, much stronger compound compared to cyclohexane-135 triene. The resonance, these bonds constantly switch over and they allow aromaticity to happen. Furthermore, right, that's just one thing. They also have we had here these p orbitals, right? And these p orbitals, they look like clouds, right? They look like clouds. The reason for it is that as I said before when I was talking about what was it? I was talking about I was talking about lone pairs. I think it was shapes of molecules, right? The electrons occupy orbitals, and more importantly, they occupy what we call as charged clouds. Now, what I remember from that video, or what I remember generally from charged clouds, is just that charged clouds are just an area of space where there's 95% probability that you can find an electron. You don't need to know that about charged clouds specifically, because I don't think there's going to be asking questions about charged clouds. But the idea that you need to understand about charged clouds is that there's a possibility, there's a 95% probability that you find an electron here. But more importantly, electrons randomly, there's a 95% probability that electrons will be here, but we don't know the exact location of this electron. It randomly moves here. It randomly moves here. It allows for it to constantly overlap, right? That constant overlapping, and that's what allows, because it's constant overlapping. It can't go do this. Technically, it's doing this, right? But you can't really see it. But in reality, it'll be straight. It'll be planar. It's because it's overlapping constantly above and below the plane. Don't just say up and down. It's overlapping above and below the plane of the carbonyl ring, of the carbonyl plane, not carbonyl, sorry, the benzene plane. It's actually compressed to the point it's just a planar structure. It's perfectly straight, perfectly planar. And I'll go through this. So it has actually a perfect bond length, perfect bond angle. Actually, I'll go through that, which isn't the same as cyclohexane-135 triene. The reason why I'm telling you all of this is because you need to be able to compare this compound to cyclohex. We need to compare benzene to cyclohexane-135 triene for your exam, and I'll do a conclusion at the end of the video to kind of compare the two. I'm just kind of giving you the raw points here. I'm trying to go as slow as I can. If this is too fast, guys, leave a comment in the description. I can always try and make this video explain it in another way, but that's the best way that I can do it from there. Right. So when I say that these bonds are resonating, right, think about they're resonating so fast. Actually, I can't. This is actually a slowed down version of the bonds resonating. I would have liked to have shown you a much slower version of this, where it shows you they're going from here to here, here to here, here to here, here to here, and all three bonds doing it at the same time. So we're going from there to there, there to there, but I can't. But this is still a very, 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 very slowed down version. It doesn't look like it, but this would be a very, very slowed down version to show you that they're going from here to here, and they're actually resonating, jumping from each side. And when he actually does that, when I say it allows aromaticity, it allows it to be a stable ring structure. That's what all aromaticity is. Aromaticity just means a stable ring structure. That's all it means, right? And that's because what I mean is it's stable because the bond length, right? Imagine, let me put it back here, right? This is not a double bond. This is not a double bond. This isn't double. Because this is constantly moving here, it's almost considered to be like every bond is a double bond, because this will constantly keep switching. At some point, within a picosecond or so, it will become a double bond. And that's why it's one of the features of it, which I'll go through it, is that they all have the same bond length. You would expect that this bond length is different to this bond length because one is a double bond, one is a single bond, right? But you have to imagine this compound as every single bond is like this. And the best way to actually represent this, because it doesn't look like it makes sense, but the best way I can explain this as I can example is like, think of like a helicopter ring, right? think of helicopter propellers. Think of helicopter propellers, right? I'm trying to make not to confuse people too much, but think of it when you think about helicopter propellers when they're stationary, you can clearly tell that where the propeller is, that there's a massive gap in between each propeller, right? It looks like there's a massive gap in between, and it's very easy to see that it's not a circular ring. It's free, it's free kind of like lines that goes out like that, right? And it's not a circle. However, when the propeller starts to move really fast, and I see really fast, like when they're actually in the air or when they're about to pull off, it looks more like like this, right? Or that's a horrible circle, but the idea is that you can see like a circle, and it actually looks more like the propellers in the ring look more like that. They don't look. You can't. It's not easy to tell where the propellers accurately are because they're spinning so fast. They're spinning constantly so fast. You can't accurately tell where, and it looks like a ring. It looks like it's a ring, and that's because the blades are constantly in every position all the time, and that's what you have to imagine benzene is. Although technically, theoretically, right? Theoretically, they're not at every position all the time, but in hindsight, in reality, they kind of are because the time difference for it to get to here is almost instantaneously. And one of the features are that the bond angles are all perfectly the same, and actually bond length is the same. And the way we represent this idea of it being constantly in resonance and the bonds are constantly switching all the time is this circle. So to represent the mobility of the bonds, the mobility, i.e. the resonance of the double bonds in benzene, we draw the benzene with a ring as shown above. We call this alternation of double bonds resonance. The skeletal structure is just an average structure to show the double bonds moving around the whole ring. This ring just shows that the bonds are constantly moving around the whole ring, and it probably, if I was to imagine looking at it, it probably would look like this, because the bonds are switching so fast. It would just look like I said before, like helicopter propellers. They would be spinning around this not spinning, but you know what I mean, alternating so much, it would look like just a ring constantly circling around or constantly just here, or like a helicopter just constantly moving around. That it looks like a ring. Hopefully you understood what I was talking about here with the propellers. I just tried to give an example to try and help you understand, right? But yeah, when you're doing the mechanisms, or when you're drawing benzene, you constantly see this compound, right? Or you'll see, maybe if you ever seen an example, I don't know, example of I think aspirin has a benzene ring in it, but don't quote me if I'm wrong, right? But there's definitely been comments where you've seen this ring structure. What was that structure called again? Was it Terylene? Kevlar. There we go. Kevlar has a benzene ring in it. I'm pretty certain it does have a benzene ring in it. If I'm wrong, I'm really disappointed in myself. But I'm pretty sure it does have benzene ring in it. And that's all this compound is, and that's what the ring represents, that resonance. And yeah, you can, in your exam, you can represent it like this. You can ideally do it like this, because this is the easiest way to make sure you get them up all the time. You can represent it in the Kekule structure, that's what it's called, where it's without these arrows, obviously. It looks like this. It looks like cyclohexyl-1,3,5 triene. Ideally, when you're doing mechanisms, it can work. They do allow it in the mark scheme, but you'd be causing us. I'd avoid it, really. In my opinion, you can look at the mark scheme and how to do it, but you're always gonna get it right if you just. I mean, you're gonna get it right doing it this way. And it's much easier to remember. All right, so I've done talking about that, right? I know. I'm gonna talk about substitution reactions, because benzene's most stable structure affects its reactivity. Benzene reactions are typically not. Benzene reactions are typically substitution, and typically electrophilic substitution, right? Because benzene is well, benzene. Oh, actually, no, I'll just say it right here. Benzene will always react with an electrophile. It will never react with a nucleophile, generally. And if it does, I mean, would it ever do it? If there's a side group attached to the benzene, then it might do nucleophile. It might react with a nucleophile. But in itself, right? As I said before, it's so nuclear. This compound, if it has been made obvious already, is so nucleophilic. It's so nucleophilic. Reasons why, I just said it already. Each carbon has 3 bonds. Donates 1 electron to form a delocalized pi system. There's a delocalized pi system here, and it's so that benzene is considered to be very electron dense, very electron dense. So it would substitution is the reaction, as I said before, and I said the reason why, but it would always be electrophilic substitution. It would always be electrophilic substitution because it's so electron dense. Another thing you need to kind of, well, you don't need to know it, but you may need to know about it, about benzene, right? And it structures that if you was to burn benzene, I don't think it's ever come up in an exam, but in case it does come up, if we're talking about density, if you're able to burn benzene, you'd pretty much always do incomplete combustion because it's so carbon dense. It's so carbon dense that, oh, let me get that back. There you go. Probably leave that as that. It's so carbon dense that there's just not going to be enough time for all the oxygen to completely combust, or not burn, completely combust with all the carbon atoms. So yeah, incomplete combustion only. But now I'm going to go back into substitution reactions, right? So benzene's stable structure affects its reactivity, and benzene's reactions are typically substitution and not addition. So you would expect with I mean, as I said, well, this isn't cyclohexyl 135 triene, but it looks like the exact same structure as cyclohexyl 135 triene. But cyclohexyl 135 triene, or alkenes, would generally do electrophilic addition because that's what they do, right? They can it's perfectly fine to break the double bond and then just form to form an alkane. Really, you're forming an alkane. However, benzene doesn't want to do that. It wants to constantly get those double bonds in resonance to maintain the key word here when talking about benzene is maintaining aromaticity. And to maintain aromaticity, you have to have those p orbitals overlapping one another. Those p orbitals overlapping above and below the plane of the benzene ring. You want to have those double bonds in resonance. If you break the double bond, and you have other side groups on each carbon, which would disrupt the p orbitals overlapping above and below the plane. Therefore, so if you don't have the double bonds, there's no resonance. You have resonance from here to here, but you wouldn't you have complete resonance. So it doesn't want to do that. It wants to maintain this ring. It wants to maintain this resonance. It wants the p orbitals above and below the plane. It wants that aromaticity. That's the key focus whenever you're answering these questions. I'll go through how to answer this question if we're going through how to go through every single point at the end. But the whole idea to understand is that you want to maintain aromaticity. So, so this is different from alkenes, which normally undergo addition reactions. Substitution is favored because it reestablishes the original structure. So in benzene, you're still reestablishing the structure. You have the side group that's bonded to it, but you're still maintaining this aromaticity here. So it reestablishes the original structure and so retains the very stable aromatic structure. So here I'm going to go through it. I'm pretty sure I should be going through this in the next video, but life is short. So, the first thing you need to go through, will I go through it properly in the next video? Let me double check. Do I go through it properly in the next video? I do go through it properly in the next video. Oh yeah, I do. Well, I'll give you a brief overview. I'll give you a brief overview as to what happens, right? So, because, as I said before, benzene is acting as the nucleophile here. It'll be going from that's what I say you can draw as that's what I said I prefer drawing a ring. I'll explain why it's easier to draw as the ring than this, but technically this is coming from one of the electrons from the double bond going to the Br plus. Remember, these bonds are in resonance, that's why it's the ring. It looks a bit silly when you're thinking about it as well. Why not just do the double bond to show exactly where it's coming from? But remember, the bonds are in resonance, so I can't say the bond is here, because technically the bond's gone away from here. It's still here because it's obviously it's constantly, the double bond is technically constantly in every single bond, but it's not really, isn't it? It's alternating. It's just happening really, really fast. But I say drawing this as a ring is a better way of describing it. It's showing that the aromatic, that resonance is still there, the double bond is there. But just to show you, it's just a better way of showing it. It's a more correct way of showing it. It avoids all this this side, bullshit. Really, as call it. It can be kind of confusing. So I always just represent it as the ring, right? But anyway, talk is talk. I'm gonna stop talking here, but. The first thing you have to do is actually form this Br plus, this electrophile. And the Br2 reacts with aluminium chloride catalyst to make an electrophile ion of bromine. So you want to form the electrophile bromine ion, Br plus. So going from the double bond, from the bond from benzene, or from the benzene ring, forming this Br plus here. You've temporarily, there's like a little intermediate, that's the word. You temporarily break aromaticity and you form this little intermediate. Now, this little ring here, it gets broken into 2/3. In the exam, what teachers say is 3/4, but really, you only have 3 bonds in benzene, so technically, it's 2/3. So I guess I'll do add a little bit more to here, just to show you. But 2/3 or 3/4. Anyway, in the exam, when you're doing this actual thing, they'll say anywhere between 2/3 and 3/4. It's just showing that you've broken one of the bonds temporarily in the intermediate, right? And now you have this H here. Remember, each one has a. I'm not representing the H because this is a skeletal structure, right? But there's a H on every single one of them. But here in this example here, we have the H and the Br, both here. But remember, we need to reform aromaticity. This isn't stable. This is really not stable. So what it will do is that this carbon-hydrogen bond here will break, and it will. You've given an electron. Because if I break this bond here, right? This makes more sense. Breaking this bond makes more sense because if I break this bond, the electron would go to technically the Br because bromine is very electronegative. Would this be this? I mean, this has got quite a strong withdrawal effect if I'm being honest. But breaking this would just reform what we already had, right? But breaking this here just makes more sense. Non-polar bond, and also hydrogen would doesn't want to form H minus. It wants to form H plus, right? So break that bond here. Now you can maintain this here, but now the electrons come back to the aromatic ring. Resonance is reformed. Aromaticity is reformed. So resonance is re-established and aromaticity is reformed here. And now you have the benzene ring is back to where it is, and a Br bond here, right? And that's all it is. I mean, I'm gonna go through it I'm gonna go through it each step where the mark actually is in the next video, because this is a video about talking about that 6-mark question where I talk about the structure of benzene. But this is just a brief video, just a brief part of me just showing you that it does electrophilic substitution reactions, how it has this little ring from the ring to the Br plus, breaking this carbon hydrogen bond to reform aromaticity. Because remember this, when you've bonded that there, you've broken the ring in this little intermediate here. How you have this here, breaking this bond to reform aromaticity. Aromaticity is reformed or reestablished, and now we have bromobenzene or phenol or I call this bromobenzene. 1-bromobenzene. I forgot how to name benzenes. I know that's like phenyl groups. I already have that now. 1-phenyl benzene. I'm not gonna call that 1-phenyl. 1-bromobenzene. I guess I'll probably call it that. Yeah. So this is not correct. Just to make this clear. This is not how you do it. You wouldn't represent it like this. So if it was to, well, this is more partially positive. Yes, it would break fine. But this would never happen because bromine when you have this broken here and you're forming Br minus. But by the way, bromine can be either Br plus or Br minus. It can have actually either property. But when you're forming Br minus like this in a nucleophile, the reason why this is never correct, don't do this. Bromine is a nucleophile here. This is much more nucleophilic than this. This would just repel this. This would never form. So, you'd never have this kind of take this away and then you have bromine here. That would never happen. So I only say this because I've seen some people get confused when they see sodium bromide. If they ever showed you examples that you have just your, they'll make it very clear what's the electrophile, and it'll just have that one electrophile reacting for electrophilic substitution. It's not, it's not electrophilic addition and elimination. I guess this is what will be called here. No, it's just electrophilic substitution, and that's all benzene really does. Benzene in itself, right? I've kind of gone on for that for a little bit too long. How long is this video now? 30 minutes, damn. Okay, I need to kind of hurry this up now because I don't want to spend too much on this. But evidence of the structure of benzene, right? So many pieces of evidence have been used to prove the structure of benzene. So this is the structure of benzene, right? So this geezer, top lad, one of my favorite like scientists of all time. His name was Kekule. He's a German. I think, was he Austrian? I'm pretty sure he was a German side, but if he's Austrian, my mistake. But yeah, he's the one that came up with basically. So what happened was, right, is that benzene in itself, the benzene or people discovered they didn't understand it as benzene. It's him that understood it as benzene, right? There's a reason why I'm saying this story, right? But this is the history of it, right? So people discovered this property, and it's kind of related to what I'm going to be talking about here, about that the enthalpy hydrogenation. It had a property of that they believed it was cyclohexyl-1,3,5 triene, but it didn't have properties of cyclohexyl-1,3,5 triene. It had some things that were similar to cyclohexyl-1,3,5 triene, but it wasn't behaving like cyclohexyl-1,3,5 triene. Now, people for a long time were trying to understand why it was like this. They wrote journals, and it's notably, so there's two scientists that discovered kind of got into this, and so notably the Scottish chemist Archibald Cooper and Austrian scientist Joseph Loschmidt, by fabrication story of two daydreamers here about whirling carbon atoms forming chains. So Kekule, so they believe that Kekule kind of stole their idea really, but about this benzene structure, right? They believe he stole the idea by saying that. I'm kind of going over the topic. Kekule had this dream, right? So Kekule comes along. I'm kind of messing up the story now. It's actually going to be a really good story, but I kind of gone over the top here. But yeah, so these two scientists kind of had this idea. They're kind of quarreling about how the structure of benzene really is, because they didn't. No one knew how it's possible, how it could be somewhat similar to cyclo-1,3,5 hexatriene, but wasn't behaving like cyclo-1,3,5 hexatriene. Kekule comes along, right, and he says that he had this weird dream. It's a dream about a snake biting its own leg. Oh, biting its own, not leg, sorry, biting its own tail. Like, imagine a snake biting its own tail. So I have like this part here, terrible snake, right? But it's now biting its own tail. That's what he imagined at night. Weird dream, right? But he used that as inspiration, as saying, he fabricated a story of two daydreams he had about whirling carbon atoms forming chains. He imagined this snake as whirling carbon atoms as a chain, right? So imagine a straight chain, right? And he's now got this snake he's got this snake, and he's representing the snake as a carbon chain. Now this snake, right, that's now a carbon chain, is now biting its own tail, right? And the reason why I'm saying this, right, is that it's twisting and turning like snakes. The twisting and turning like snakes part is to show the resonance. That's why he kind of made the link. It's believed. Don't quote me on this in case I'm wrong, but it's believed that he was referring to resonance when he's saying that it's like a carbon atom. Well, a snake kind of moves like this, right? It's kind of always moving like that. If this snake, right, that's representing carbon atoms would bite its own leg, it would still kind of maintain this kind of, it still has this weird kind of like twisting and turning like a snake. And he's saying just like a snake that's biting its own leg is still twisting and turning, that's what benzene is. It's twisting and turning, and the twisting and turning is the resonance. Is this. And he said that's what benzene is. He said that benzene is now it's cyclohexyl-1,3,5 triene, but the bonds are constantly constantly switching in resonance, and the bonds are actually the same size, the same bond angle, and it's because the structure of it is constantly shifting, right? And I'll show you an example of what I mean here. It's doing this. Now, you can't see the naked eye, wouldn't be able to see this. You wouldn't be able to see this because it's happening way too fast, but he's saying that it's doing that, but to the naked eye, it would look straight, flat, and planar. It's just happening so quickly, we wouldn't be able to see it, right? But it's flat, planar structure, and it's because it's moving around, it's able to fix itself in this, into this kind of wedge shape, and it's constantly got bonds of same length, or appears to look like same length, and it has this very stable structure. So I mean, those two scientists kind of denounced and said that he copied the idea really, but yeah, I mean, his little snake thing was kind of right in it. So yeah, nice weird beard. Cool. So for years, chemists argued over what the best structure was to represent benzene, which is what that story was there. So benzene, right, the most important part about benzene is that it has carbon bonds they all have the same length. So all carbon bonds have been shown to be the same length. So this length is the length of each carbon. The length of each carbon bond is 139 picometers. You have to know that, or 0.139 nanometers. And it's somewhere between. It's shorter than a carbon-carbon single bond, and longer than a carbon-carbon double bond. So it's this in-between part here, right? So I can't remove these. It's somewhat in the middle of between being because benzene because it's constant resonance, right? It's believed that all bonds are the same length because they all have really they all have the same bond. It's actually all the same bond. So all have the same size. The size of each bond is precisely 139 picometers. You don't have to know about this one here between carbon and hydrogen being 109 picometers. That's not really relevant, but this carbon bond here in benzene is 139 picometers, and it's because it's longer than it's shorter than a carbon single bond, but it's longer than a carbon double bond. And yeah, as I said before, that's why I don't like representing it like this, because if I was representing it in the Kekule method, though I like Kekule, I don't like representing it like this, because technically this bond is much shorter than this bond here, but the ring would be a perfect way of showing benzene, because it shows that all bonds are, though this is happening, the constant resonance actually make sure that it's they're all the same size. It's a mix between this bond length and that bond length, and it's they're all bond lengths are the exact same size. And then if I go into the next part, right, bond angles, they all have a perfect bond angle of 120 degrees. So the structure has been proved to have a bond angle of 120 degrees at each carbon, and this means the structure must be planar. If sorry, if the bond angle, if the size of each bond is the same, and the bond angle is the same, and each bond angle is the same, therefore this structure has to be planar. Mathematically, it has to be planar. If any shape has the same size and the same, in maths, it was in GCSE maths, if any compound has the same size of each side, the length of each side is the same, and the bond angles of each side is the same, mathematically we can describe a compound like that as being, or in this case, planar. The planar part is more to do the scientific part of it, but we know that it's flat, and we know that each bond angle is the same. We know that the size of it is the same, so we know it must be planar. The reason why I'm kind of overemphasizing every point, because I'm just trying to make this is the first time you hearing about this, so I'm just trying to emphasize and hit home that point. So okay, right. So this is one of the things that's the biggest way of showing the difference between the biggest physical thing of showing between the difference between benzene and cyclohexyl 1,3,5-triene, because all the other things are more to do with these are technically intramolecular forces, right? So those are chemical properties. So everything I've described to up until this point, really, I mean the bond length, yes, I guess technically that's physical property, but really all these things are chemical properties or chemical reasons why they're different. But if you want to have a very easy to see physical difference between the difference of cyclohexene, so cyclohexa 135 triene and benzene, and that's the enthalpy of hydrogenation. Sorry, I kind of butchered the name there. So the enthalpy of hydrogenation of benzene is more positive than of cyclohexa 135 triene. This is an exothermic reaction because you're forming bonds. Basically, all hydrogenation is just adding hydrogen to each. It's just adding hydrogen to the structure, so that to adding hydrogen to each carbon atom so that it forms cyclohexane. You're converting cyclohexa 135 triene into cyclohexane and benzene into cyclohexane. But the enthalpy of hydrogenation for benzene is more positive than cyclohexa 135 triene. So benzene is less prone to hydrogenation because you're actually the enthalpy hydrogenation for benzene is more positive than cyclohexa 135 triene. That means it's more stable. Why? Because less energy. If this is more negative, that means that more energy is being released. The reason if more energy is being released, it means, remember, bond forming is an exothermic process, right? So if more energy is released when the bond is being formed, it usually means that it's easier to form that bond. If more energy is released to form that bond, right, it's easier to form that bond. So this here is less exothermic, it's less negative. It means that less energy is released when the bond is formed, and that's because it was much harder to actually form that bond. And the reason for that is because benzene is less prone to hydrogenation because it breaks aromaticity. Hydrogenation is a form of addition reaction. As I said before, benzene tends to do substitution reactions. So this breaks the aromaticity of the benzene ring, which is quite unfavorable. So this reflects how benzene is more stable due to the aromaticity. So you represent this as 3H2 because it's one for each hydrogen. So for benzene, the enthalpy of hydrogenation is minus 208 kilojoules per mole. You have to know that, or they'll show it in your actually they show that to you in the when they present the 6-mark question to you, they'll show that to you, right? That's minus. So I just remember this off the top of my head. For benzene, the first thing you actually have to do for this, right, is that it's actually the enthalpy of hydrogenation for one carbon will be minus 120 kilojoules per mole. But because there's 3 of them, you have to times that by 3, and that's minus 360 kilojoules per mole. That's it now. So now I'm going to kind of go, and as you can see here, to form cyclohexane is much easier compared to benzene, which is minus 208 kilojoules per mole, because more energy is released when it comes to hydrogenation of cyclohexa 135 triene compared to cyclohexane. Now I'm gonna do a little overview. I haven't written it down. I just kind of decided at the end of it to kind of just do an overview. So this topic here, this is the question I was thinking about here, and yeah. So the question is, data about the hydrogenation of cyclohexene and of benzene are given, and that's the example I gave here. Explain the bonding in and the shape of benzene molecule. Compare the stability of benzene with that of the hypothetical cyclohexa 135 triene molecule, and use the data in your answer. Right. So first of all, the reason why I picked this question was in your actual exam they might throw it in a weird way, try and throw you off. It might change the way that it's said, but really what they're talking about is just this here. Really, the reason I picked this question is that if you understand how to answer this question, this is a 6-mark question, right? And it's one of those questions where they have to where the mark scheme is band 1, band 2, band 3. And that's how they mark it, right? But if you understand how to answer this question, really, you understand the whole of this topic. I know some people who understand this topic might disagree with me, but really and truly, in my experience, if you understand how to write this question, it includes you talking about every aspect of benzene, right, in this question, right, or the more important parts of it, then you know how to answer the question. Now, part B of this question maybe is maybe showing you a further justification, but really, if you understand this A part, you get it. Or at least from this video, the substitution part is also included in this topic, but I'm going through that in another video, right? But I'll go through this question here. So Oh, one part here. So the question was, remember, saying that explain the bonding in and the shape of benzene molecule. Compare the stability of benzene with that of the hypothetical cyclohexyl 135 triene molecule. And then you state in your answer. Right, so the first thing I would do here is that I know this is quite jarring because people hear this from their teachers all the time, right? But I'm going to say it because it's true. And the first thing I look here, I'm not doing this under time conditions. It's 6 marker, but I'm just doing this to explain the points here, right? And the first point that I talk about here is that the thing is that I look here is that it says explain. Now, what they're actually telling you that you need to know obviously this between explain and describe, but you should know that by this point right now. But it's just this explain. Describe is what you see. Explain is why is that there. Explain why is that happening, and then you have to go through it. But here they're asking you to explain a physical property. They're explaining you. They want you to explain why there's a difference between this and this. Between why is that so, right? And if they're asking you to explain a physical feature, really what they're saying is, or what they want you to say, they want you to explain. They want you to explain the chemical feature. If someone wants to explain the physical feature, really what they're saying is they want you to state out the chemical feature, because the physical property is there because of the chemical features, right? And that's all it is. Explaining the physical property here, or just be explaining what the chemical, just stating out the chemical properties, right? So explain the bonding in and of the shape of benzene molecule. Compare the stability of benzene with that of the hypothetical cyclohexyl 135 trimolecule. So the second part of this is actually the comparison. Oh, yeah, I already done that. It's the comparison. Compare. So if you explain this part here, but you don't compare with that of cyclohexyl 135 triene, you haven't actually answered the question. Or you haven't fully answered the question. You're maxed out at band 1, I believe, because you haven't answered every. Yeah, you'll be capped at marked at band 1, which is like 1 to 2 marks, because you haven't answered every aspect of the question. Band 1 and 2 is answering Band 1 and 2 is answering only one aspect of the question. Band 2 is answering every aspect of the question, but it's poorly answered. Or it's not poorly answered, but it's not not every explanation is in great detail. And band 3 is all aspects of it is there, and it's in great detail. And that's what I'm going to try and do for you here today. So the first thing I'm going to talk about here is that saying, I'm going to talk about the structure here. So the first thing I'll talk about here is the structure. Now, in your exam, when you're actually writing this, you can actually just do it as bullet points. I'm doing it as bullet points, but not the bullet points as in the actual full-on answer. I'm just giving the abbreviated points, and I'm going to explain what it is, because I can't bother to write every single point. But benzene's structure is the first thing I'll be talking about here, right? Now, actually, no. So actually, that's not the first thing I talk about. The first thing I acknowledge, right, is the enthalpy of hydrogenation. The first thing I acknowledge here is that's a terrible triangle. Enthalpy of hydrogenation. That's because benzene's enthalpy of hydrogenation, right? Benzene's enthalpy of hydrogenation is minus 208 kilojoules per mole. Whereas cyclohexyl 135 triene, right, is, so I'm just going to say C because I'm not able to write the entire thing here, but you know what I'm talking about, has an enthalpy change of, now here's where you have to be, this is quite important, this is actually important for the market. Here I've just did it because this is me actually answering the question, right, or this is me giving the actual phrase, but in the actual exam question, they haven't actually said 3 times by H2, they just said H2. And the enthalpy change of hydrogenation, of one hydrogenation, is minus 120 kilojoules per mole. Here, see here that for benzene, they've done it for benzene. Minus enthalpy of hydrogenation of all of benzene is minus 208 kilojoules per mole. But for one bond, if this is cyclohexene, but they're telling you here to talk about the hypothetical cyclohexyl 135 triene molecule. So you'd have to times this by 3. If it's 1, 3, 5, that's tri or 3 double bonds, right? 1, 2, and 3. Then you need to times this by 3. 1 is 100 minus 120. So then we're timesing that by 3. So the actual benzene is minus 208 kilojoules per mole. I don't know why this is shifted to the left, to the right for some reason. That's just kind of weird. Why it's just done that for some reason. Just put this back here. Right. Yeah. So the enthalpy change of cyclohexane 135 tri. Sorry, benzene is minus 208. Cyclohexane 135 triene is 3 times by minus 120, which is equal to minus 360 kilojoules per mole. Now that brings us on to now we've kind of gone on to, we've used the data to show that there. This isn't really explaining, it's just kind of just doing the calculation here. But the first comparison is just saying that, noticing that benzene. So let's say that benzene is more stable because now you have to think about this before I explain what hydrogenation is, right? And that's me saying that the benzene here, if hydrogenation is adding H2 to the carbon, right? And bond forming is exothermic. Now it's easier you're releasing more energy with cyclohexane 135 triene compared to benzene because it's easier to do that. Now I'm going to explain, obviously there's a reason for that, I'm going to explain that here, but first we're just acknowledging that there's a difference between this and this. That's the first thing. So benzene is more stable because it's, you could say the actual number, but it is 152 kilojoules per mole. I decided to do it like this, but you can just say that it's more endothermic. You can just say it's more endothermic, but they said use data in your answer, so this is how I would do it. But just saying that it's more, you can physically see it's more endothermic or less exothermic. That's also a way of saying it. But it's 152 kilojoules per mole more endothermic or less exothermic. So I could say, yeah, / less exothermic. Don't write this part. This is, you can use, this is just me saying you can use either or, than cyclohexane 135 triene. That's the first thing now. So the second part here now is saying, why is that? Why is this here? Why? Now we're actually going, we've done a little comparison here. Now you have to do this part. You have to do the comparison part first. So you don't have to do the explain part first. You can do the comparison part first and then do the explain. As long as you're answering every aspect of the question, that's fine. You can do the explain part first and then do this part at the end. I prefer doing the hydrogenation part first because it allows you to say, here's the obvious reasons. This is the obvious reason here. Why? This is the obvious difference that we can see. And now I'm going to explain why there's a difference and why it's more endothermic. It's more endothermic or less exothermic. So I say this is because. So this is because, and then because. And now the first thing I'll talk about here is benzene's shape. So benzene's shape, right? Benzene is, but it's because, so benzene's, so now I'm going to talk about, don't write down benzene shape. I'm going to start talking about benzene shape. So benzene shape is a hexagonal ring. So it's not shape, sorry. Benzene's structure, I should say. Benzene's structure. Is it shape? Yeah, I call this more structure than shape, really. Benzene structure. So hexagonal, it's a hexagonal ring, right, with each carbon atom has 3 bonds and donates 1 electron to form a delocalized pi system. You could call it a pi. I mean, you could call it. There's other ways. I mean, it's technically a pi cloud. It's two pi clouds that are kind of keeping it. Oh, that's it's kind of wedging it in the. I haven't got the shape here, the diagram to show it, but I just call it as a delocalized pi system. I mean, that's how I'd call it. It's a delocalized pi system. So each carbon atom has 3 bonds and donates 1 electron to form a delocalized pi system. And the second part saying here, no, the next point saying is that is with double bonds in resonance, to form to establish aromaticity. And then more importantly, p orbitals above and below the plane. So I'm just gonna say, you already know, I'm not gonna write that down well, but it mentioned the p orbitals above and below the plane of the carbonyl of the benzene ring, to make sure that it's planar. So p orbitals. I guess I will write down above and below the benzene ring plane. Benzene ring plane. To make it structure, to make benzene planar. Now you don't need to have a crazy comparison here, because all we really see is that really the cyclohexane-135 triene doesn't have a delocalized pi system. So there's no resonance. Has no delocalized pi system, and no resonance. Or no double bonds in resonance. Now, and then the last thing that I've kind of given you every single point here. You don't actually have to say every single thing here, but you can probably get away with just saying don't probably have to say the double bonds in resonance part, but you can probably just say the delocalized pi system part and the p orbitals part. That's more important, and the hexagonal ring part. But I mean, they can't really take away marks for you saying that. It's really just more about space. And then the last 3 things that I'll talk about here is its shape. So benzene's, sorry about my handwriting, but benzene's shape. I'm already saying what I'm talking about anyway. But benzene's shape, right? It's when I'm talking about the shape, I'm talking about the bonds here, and it's got a bond length of, so first of all bonds in benzene are the same length. So that same length of 139 picometers, or 0.139 nanometers. And that's saying that it's smaller than, it's shorter, so that's shorter than, I can't write it, can I? So that's shorter than a carbon-carbon single bond, but longer than a carbon-carbon double bond, right? That's mentioning the bond length there. The second one is saying that they all have a bond angle, all have the same bond angle. Again, I know my handwriting is terrible, but I'm saying it out loud so that you can understand what I'm trying to say here. All have the same bond angle of 120 degrees. Therefore, benzene is planar. And then saying that cyclohexyl 135 triene, not all bonds have the same length, so not all bonds have the same length. And obviously they don't all have the same length, and they're not the same length as benzene, so not all have the same length. And more importantly, bond angle is not 120 degrees, it's like 109.5. So bond angle isn't 120 degrees and not all the same. And they might all be the same. They might all be 109.5 degrees. I wouldn't go for the same, but the bond angle isn't 120 degrees, and it's not planar. That's the more important part of saying, and not planar. Now I'm going to go into the mark scheme here because to see how similar they were. I've probably done a little bit too much, but I'm just showing you everything that you could write, everything that you could possibly write about this question here. It looks like a lot, but really, my handwriting is quite thick and there's not a lot here, but it's not actually a lot here. Look how short the lines are anyway. But anyway, where was I? Where was I? Yeah, it's here. Yeah, so go here, mark scheme. Yeah, see, so here, band 1, band 2, and 3, band 0 just will, level 0 just be nothing less relevant. So the first mark here is they go straight into the bonding part, right? And that's this part here. Each carbon atom has 3 bonds. That's a mark. That's kind of it's not a mark because we do the marks by the band, right? But at least we've mentioned the first part. A, spare electrons. Remember we said that in a p orbital. Yeah, we mentioned that. So spare electrons form a delocalized pi. They call it a form of pi cloud, but mentioned the spare electrons, and then there's this overlapping p orbitals. I didn't actually mention that part. I forgot to mention that part. P orbitals overlap. I should have mentioned. That's a quite important part here. I forgot to say that overlap. That's a very important part there. I forgot to say that part here. The p orbitals overlap above and below the plane. I did mention that in my when I actually did the video, but yeah, it's tired. It's late. It's late. I'm tired. There you go. But yeah, so there's each carbon atom has 3 bonds. Spare electrons in a p orbital, they overlap to form a pi cloud. They've put it in brackets, so it's not necessary, but the spare electrons and overlapping is quite important there. But they have the delocalization is important, and I have said that it has a delocalized pi system, and that is allowed. You can mention that. Yeah, I said a delocalized pi system, so you would get the mark for saying that. The next part, they got on to the shape. They said all bonds it's planar first. We've mentioned that it's planar. Benzene is planar. Hexagonal ring, a 6 carbon ring, 120 degrees. Mentioned that part there. C, carbon bonds are equal in length. So also in benzene, carbon bonds length between single and double bonds. That's interesting. So they actually talk about the actual size of the bond, which is interesting. I thought they had to say that, but that's fine. And then the third part is about the actual stability and saying that the expected hydrogenation of cyclohexatriene is minus 360 kilojoules per mole. So working out that part, working out the front minus 360 kilojoules per mole part is important. And then that's the nth of hydrogenation of benzene is, you can say less exothermic, but just saying by, but they put it in brackets here, but it's by 152 kilojoules per mole. Benzene is lower in energy than cyclohexatriene, so therefore benzene is more stable. Yeah, benzene is more stable. I put that there. So that's all the marking points. I've kind of gone above. I would have got 5 marks out of 6 here because I didn't mention this overlapping part here, but more or less I've covered every single thing. I've covered every single part here, so I've at least got band 2. I've mentioned it in great detail. So I'm band 3. but I've missed out one thing, so I've put myself in 5 marks rather than 6 marks. But if we're here, you see how you have laid it out. I've put it out into each section. I've done it in bullet points. It makes it much easier for a person that's marking your paper to give you the marks. Where if you do it in a long essay kind of thing, where it's long in prose, you might have the right answer because they should still mark in the same way, but they're more likely to make mistakes. And in your real exam, they might have to go for the purpose of the point of what's it called, remarking your paper, because you might miss out a marker, right? So doing it like this just makes it much easier. You save a lot more time writing it like this, and you feel more confident when you're writing. You say, I definitely covered that point, I definitely covered that point, definitely covered that point. And yeah, that's it. Hopefully this video was helpful, and I'm done.